Okay, so you ready? Yes. So welcome everybody. Good afternoon, good morning, and good evening to everybody from all over the world. So I'm Yuankai Chen from Taipei, Taiwan, and I'm the moderator of the talk. So I'm very happy to introduce Professor Alexander Efimov from HSE University. HSE stands for High School of Economy in Moscow. So he's going to talk about on the K-theory of large triangulated categories. So please, thank you.
Thank you very much for the introduction. So I will, so here are the slides. I'm very happy to speak at the ICM, my talk will be about K-theory of large triangulated categories. So I will basically sketch this. Sketch this new notion. Why is it? How to define such K-theory, and why is it reasonable to consider, and some interesting results about it. Okay, so the plan of the talk will be the following. First, I will very briefly recall the classical Grothendieck groups for associative ring, for abelian category, and for a triangulated category. Then I will briefly mention, without going into details, the higher algebraic K groups and also the negative K groups. Then I will motivate and sketch this definition of this relatively new notion of continuous K-theory for a certain class of large categories for which the naive K-theory just gives zero always. And this class is called dualizable presentable categories. And then I will formulate some results about continuous K-theory. First, which is already quite interesting, is the computation of K-theory for the categories of sheaves on locally compact Hausdorff spaces, and also a very recent result, about a month and a half old, about continuous K-theory of categories of nuclear models on formal schemes. So these are also relatively new categories defined by Clausen and Scholze in the framework of condensed mathematics. And finally, to give you an idea of how this works, I will sketch more or less self-contained computation of the continuous K-theory for sheaves on the real line, say for sheaves of modules over some DG ring. So first, the classical Grothendieck groups. So for associative ring, this group K0 of R is generated by the isomorphism classes of finitely generated projective models, and by default, I will also always consider right modules. And the only relation is that the class of the sum of P and Q is the sum of the classes of P and Q. Then for abelian category, the group K0 is defined similarly, but now instead of direct sums, we have short exact sequence. So for any short exact sequence, we just impose a relation that the class of the middle object is the direct is just the sum. It should be not the direct sum; it's just the sum of classes of X and Z. Now for triangulated categories, the definition is essentially the same, but now instead of short exact sequences, we have exact triangles. And these notions of Grothendieck group are compatible with each other. So first, if you have abelian category and you take its bounded derived category, then the Grothendieck groups are the same, and the class of a complex of objects goes as usual to the early characteristic, but early characteristic in the K0 of A. And for a ring, similarly, so we have this triangulated category of perfect complexes, which are just bounded complexes of projective R modules. And again, we have identification of K0 groups, and the class of a complex P just goes to the, I'm sorry, it should be alternating sum of classes of the terms of the complex. So it's again kind of early characteristic. And in particular, if our ring is right Noetherian and has finite global dimension, then these three versions give the same answer. So K0 of the ring R is the same as K0 of the category of perfect complexes, and the same as the K0 of the abelian category of finitely generated modules. Okay, now, most frequently the K-theory, people are interested in the K-theory of schemes. And for a scheme, let's say quasi-compact, quasi-separated. So in particular, this of course includes some usual schemes of finite type over a field. The usual definition is that K0 of a scheme is K0 of the category of perfect complexes on X. And of course, if, for example, X is quasi-projective, we can just take K0 of the category of vector bundles with exact structure. If a scheme is also Noetherian, then we have another important version of K-theory, which is often called G-theory or K-prime theory, which is K0 of the category of coherent shifts, the same as K0 of the derived category of coherent shifts. And now, if we have some Noetherian scheme and a closed subset, we have this right exact sequence. So it's not short exact sequence, it's only only right exact. So G0 of the subscheme, which is the same as K0 of the category of coherent shifts with support on Z, goes to G0 of X, goes to G0 of the open complement of Z. And more generally, kind of abstract version of this. So there is a notion of a third subcategory of abelian category. This is just a subcategory closed under taking sub-objects, quotient objects, and extensions. And then we have exact sequence, again, exact on the right. So K0 of B goes to K0 of A, goes to K0 of the quotient. And this quotient is a third quotient. Basically, it's obtained by inverting morphisms in A, for which kernel and cokernel live in B. So it's a standard construction. And similarly for a triangulated category and full idempotent complete triangulated subcategory, we have exact sequence of the same sort. And here, the quotient is the Grothendieck quotient, which is also a triangulated category. And now it is well known, and I will not give the details of this, that this definition of K0 can be extended to higher K groups. So for associative rings, there are actually different approaches for the definition, but kind of original approaches that for associative rings, this is done by equivalence plus construction, for abelian categories by equivalence Q construction, and for triangulated categories which with at least some kind of enhancement, at least enhanced over spectra, but I will mostly talk about differential graded enhancements. So it's done by Waldhausen's S construction. And they're again compatible with each other as for K0. One of the most important properties, and it's actually a defining property if you approach it in a universal way. One of the important properties is the localization sequence. If we again have enhanced triangulated category and some subcategory which is idempotent complete triangulated, then we have now a long exact sequence. And here, it actually, the last map is surjective because I'm taking just the usual Grothendieck quotient and I'm not adding direct summons to it. Okay, and now it is important that this can be naturally extended to all integers. So we can also define negative K-theory. And for this, an important observation that if triangulated category has at least countable direct sums, then K0 equals to 0. And this is the standard argument, often called Ellenberg swindle, that if we have any object, then we immediately see that the class of the countable direct sum of copies is the same as this class plus also the class of X itself. So which immediately implies that the class of any object is 0. And you can do the same, but just apply all the same to the identity functor. It shows that for enhanced triangulated category with countable direct sums, we have the vanishing of all key groups, in fact. And this allows to define negative K-theory, which is due to Schlichting. So one way to do this is you take a enhanced triangulated category, some perfect complexes over some DG category, and then define the Kalkin category, which is Karoubi completion of just formally adding direct sums of idempotence. So completion of the quotient of all modules by perfect modules. Here I ignore set theoretic issues for simplicity. I mean, you don't need actually all modules. You can restrict with sufficiently large subcategory, but let's ignore set theoretic issues. So we have this short exact sequence, which essentially forces us to define the minus first K group to be K0 of this Kalkin category. Then we can iterate this and define K groups for all negative integers. And so we have K groups for all integers. So the terminology, I will briefly just mention that I call this Kalkin category because by analogy with functional analysis. So if we have a field in the vector space, then in this Kalkin category, endomorphisms of vector space will be just usual endomorphism modular maps of finite rank, which is just V star tensor V. And this is algebraic version of the usual Kalkin algebra of a Hilbert space, which is the quotient of bounded operators by compact operators. And compact operators is just the closure of bounded operators of finite rank. Okay, so summarizing what we just said, so for enhanced triangulated categories, we have K groups for all integers, and short exact sequence of triangulated categories with enhancement gives a long exact sequence of K groups. We have actually a more refined invariant. I mean, how originally all of this was defined, that we have a non-connected K-theory spectrum whose stable homotopy groups are given by K groups. And for a short exact sequence of enhanced triangulated categories, we have just exact triangle in the category of spectra, which in particular implies the long exact sequence of K groups. Now I will explain the motivation and also the logic behind the relatively new notion of continuous K-theory for certain large categories. So as I mentioned, the naive K-theory of large categories vanishes. So let us recall that the notion of compactness for objects. So if you have some cocomplete triangulated category, it doesn't even matter if it's enhanced or not. Cocomplete just means the presence of infinite direct sums. An object is compact if home from this object to a direct sum, to some infinite direct sum, is the same thing as a direct sum of homes. So this is a very strong condition on X. And C is said to be compactly generated if literally there is a set of compact objects which generates C. By generate, I mean using infinite direct sums and cones. It's equivalent actually to the stating that the right orthogonal to this collection of compact objects must vanish. Basically for a small DG category B, the category of modules, I mean, of course, the correct version of the DG category corresponding to derived category of models. I'm not mentioning this small details. So it's completely generated, and subcategory of compact objects is exactly the category of perfect models. And geometric situation, so the basic class of examples is quasi-compact, quasi-separated scheme, which is essentially almost any scheme which you encounter in real life. So the category, the derived category of all OX models with quasi-continued cohomology is compactly generated, and the compact objects are exactly the perfect complexes. But in fact, some naturally appearing large triangulated categories coming from topology and geometry are not compactly generated. And the basic example is given by the theorem of Newman. So if you have a non-compact connected topological manifold, then the derived category of sheaves of, let's say, of vector spaces has no non-zero compact objects. And more generally, in fact, for some locally compact Hausdorff space X, the category of sheaves of complexes of vector spaces is just minor detail. I will for general locally compact, it's natural to consider this version instead of complexes of sheaves. I will not go into details. So it's almost never compactly generated unless X is like locally profinite set, like so totally disconnected, like for example, like counter set. Another class of examples which naturally appear and not compactly generated are obtained by imposing a single support condition. So if we have some C1 manifold and some closed quasi-tropic subset, then the category of sheaves whose singular support is contained in this subset, it's usually not compactly generated. So roughly speaking, it happens when lambda is Lagrangian with some reasonable singularities. For example, when X is real analytic and lambda is subanalytic. Another and actually more interesting, at least to me, class of examples comes from the new categories of nuclear models due to Clausen and Scholze. And these categories, I mean, they sound like functional analytic categories, but in fact, these are just usual kind of large categories, but without which are without any kind of enrichment over topological vector spaces. These categories are associated, for example, with formal schemes, and more generally with adic spaces, and also there's a more sophisticated notion of more general analytic space within this framework of condensed mathematics, and so there's also nuclear category in this generality. And it turns out that in all of these cases, which I mentioned, this large triangulated category belongs to a very reasonable class of dualizable presentable categories. Well, I should be a little bit careful with this, with what I say in the brackets, with these analytic spaces, because it's tricky. But let's say that for formal schemes and for reasonable adic spaces, this category will be dualizable. And these dualizable presentable categories, I will recall briefly the definition. They're almost as good, turn out to be almost as good as compactly generated. But still, this is a more general class. And we will sketch the definition of a continuous K-theory for such categories. Again, it's very different from the naive K-theory, which would just vanish. And so the basic properties is that if our category is completely generated, for example, modules over some DG ring, then we will get just the usual non-connective K-theory of the category of compact objects. So this superscript C means compact object. And for a short exact sequence of dualizable presentable categories, we will have an exact triangle as expected. Otherwise, it would be pointless if you don't have this property. I will very briefly recall some definitions. For a presentable cocomplete category, the kind of shortcut definition is that if it's enhanced, so it is presentable if there exists some DG algebra. Let's say we are working over some base ring, some DG algebra, and some module over this DG algebra, such that this category is just the right orthogonal to this module inside the category of all modules over A. This kind of short definition of presentability. Equivalently, this means that C is well generated in the terminology of Ammann-Niemann. I will not give details, but this just means that there is some regular cardinal number kappa, such that C is generated by kappa compact objects. Again, using cons and infinite direct sums. I should say by a set of kappa compact objects. And so a functor between such categories is called continuous if it commutes with direct sums, with infinite direct sums. So that's denoted by DG categories continuous over K, this infinity category of presentable DG categories and continuous functors. And then you have a natural symmetric monomial structure on it, the Lurie tensor product. It's a little bit simpler to describe the internal home for this tensor product, which is given just by the categories of continuous functors. And again, with this shortcut definition, this product of these categories corresponding to pairs of an algebra and a module A1 M1 and A2 M2. So you just take the tensor product of these algebras and take A1 tensor M2 plus M1 tensor A2. So presentable category is dualizable if it is just a dualizable object in the symmetric monomial category of this presentable DG categories with Lurie tensor product. And even if you don't know what is a dualizable object, I will give alternative characterization in a few seconds. So dualizability turns out to be independent on the base ring. So it turns out to be an absolute property, and also the dual categories. The dual category is also independent on the base ring. And the following characterizations I will give three characterizations out of many equivalent ways to define this class of categories. So one is just dualizability, which I just mentioned. So another that C can be represented as a kernel of localization. Namely, there is some map of DG algebras, which is a homological epimorphism, which just means literally that B tensor B over A is the same thing as B. It means that extension of scalars is localization. And so we take the kernel of such localization, and this is categories which can be represented in such a way are exactly the dualizable categories. And also another kind of intrinsic definition is that the Ionada embedding from C to modules over C. I mean, to avoid set theoretic issues, you can consider modules as int objects, for example. So this Ionada embedding has a twice left adjoint. So this is another characterization of the same class of categories. And now we call continuous functors actually strongly continuous if its right adjoint is continuous. And this is very natural notion. So we denote by this DG categories with superscript dual the non-full subcategory formed by dualizable categories and strongly continuous functors. And we have the point is that we have a fully faithful embedding of the usual triangulated DG category into this dualizable world. Just A goes to modules over A. And for this Lurie tensor product, the product of categories of models is given by models over the usual tensor product over K. And for homological epimorphism, if we have a category represented by the kernel, given by the kernel of such extension of scalars, then its dual is again just the kernel of extension of scalars, but on left modules instead of right modules. So this is a very simple description. Okay, and I should mention one more important class of examples of dualizable categories, which comes from the so-called almost mathematics. So the basic setup for almost ring theory, but a kind of version which is possibly non-commutative. So we take any associative ring and take any ideal, two-sided ideal, associative, I mean unital ring, ideal such that its square equals to itself, and it is flat, let's say, as a left or as a right module over R. And then the point is the tensor product, derived tensor product of this ideal with itself again equals to itself. And so this map from R to the quotient by this ideal is a homological epimorphism. And so we get a dualizable category, which is just the kernel of extension of scalars. This is what is known as the derived category of almost modules in this almost mathematics. And if we additionally assume that this ideal is contained in the Jacobson radical, which makes sense for non-commutative rings as well, then this category has no non-zero compact objects. It's basically just a Nakayama lemma. And this class of examples was first discovered, the class of examples of dualizable categories without non-zero compact objects was discovered by Keller, but he was working in a different terminology because I think at that time there was no term dualizable category. So it was under different name. Now, so we can define continuous case theory for this dualizable categories. So if C is dualizable, then let us choose some homological epimorphism such that C is represented as a kernel of extension of scalars. So we are forced actually to define continuous case theory to be the fiber of this map between spectra from case theory of A to case theory of B. Because I mean, we are forced because we want localization to work for continuous case theory. And also we want continuous case theory of the category of models to be just the usual case theory of the DG algebra, DG ring, let's say. We need to check that it is independent on the choice of this presentation as a kernel. And also we need to see the functoriality. It's not immediately obvious with this definition, but there's kind of more intrinsic way to define. So using what I call continuous Kalkin category, it's basically you take the image of the cone of the natural map from the twice left adjoint to the Yaneda embedding to the Yaneda embedding. So you have this map of functors. You take the cone, and you get the functor from C to, let's say, into objects of C, and you take the image, and then you complete this image. And this is just basically generalizes the Kalkin category from compactly generated categories to this dualizable context. So if C is compactly generated, we get the Kalkin category, which I described before. And this allows to define intrinsically continuous case theory. Again, I'm ignoring set theoretic issues, but they're not difficult actually here. So continuous case theory is up to a shift, the case theory of continuous Kalkin category. And the shift is just a loop spectrum, which means just the shift by -1 in triangulated category of spectra. So now, after we have this general definition, we can formulate the theorem about case theory of categories of shifts on locally compact spaces. Basically, it is given by sections with compact support. I mean, here sections, I mean, here by default, everything is somehow derived, or everything in the homotopy sense. So sections with compact support of the associated sheaf with the pre-sheaf obtained by taking case theory spectrum of A. So you just apply case theory, you get a pre-sheaf of spectra, and then you sheafify. So you have this identification. And this has a surprising corollary just in the case of sheaves on Rn. And suppose that we just have a single DG ring, so this is a constant sheaf. And so we get that continuous case theory of sheaves of modules over a DG ring is just the shift by -n in the triangulated category of K-theory of A. So it's it's iterated loop spectrum, and in particular, if we specialize to K0, continuous K0 of this category of shifts, we just get Kn of A. I mean, of course, it's not a simple characterization of Kn, because this is also quite complicated, but it's a kind of nice way of it can sometimes can be useful to reduce all K groups to K0 group, for example. And below, I will sketch an almost self-contained proof of this corollary for R, just for the real line for n equals 1. And now a more interesting and difficult problem, which was solved quite recently, is to compute K-theory of nuclear models, at least in the case of formal schemes. There's also very interesting direction in the Archimedean direction, just what happens with nuclear models and their K-theory. But I will touch here only the category of formal schemes, which is kind of much more understood. So let's take some Noetherian commutative ring and ideal, and take the affine formal scheme, which is formal spectrum of the adic completion of this ring. And the definition of the category of nuclear models is actually complicated to give a precise definition, but I will just say that it is given by analogy with a Grothendieck definition of nuclear locally convex spaces. So one possible interpretation of this category is using just very abstract machinery of inverse limits in this dualizable world. Namely, it turns out that we can obtain a slightly different category, which is larger than the nuclear category defined by Clausen and Scholze. And so this this enlargement can be described as the inverse limit of basically models. Well, here, of course, I mean DG models, so it's just complexes of models, which are just enhancements of the derived categories of R mod I to the n. But I'm taking this inverse limit, but in this category of dualizable categories and strongly continuous functors. So in particular, it's quite different from the usual homotopy limit. So the usual homotopy limit will be just complexes with locally I-torsion cohomology, and this is much more tricky. And so this is a dualizable category, and so the category defined by Clausen and Scholze embeds strongly continuously, fully faithfully into this enlargement. And so we have a very recent new result that continuous K-theory of both of this version of the nuclear category, they agree, and they're both given by the limit of K-theory spectra of the infinitesimal neighborhoods, which is R mod I to the n. And this is this limit is what people, I mean, this is much older version of the approach to K-theory of formal schemes. You just define it ad hoc, and this have a very reasonable behavior. It is much more reasonable that than naively take K-theory of perfect complexes of the formal scheme. In particular, localization works and so on. And this was often called actually a continuous K-theory of a formal scheme without any, it was actually older, so it was without any reference to this terminology. So they kind of turned out to agree in this case. I will briefly mention that we proved actually a more general statement about inverse limit, than namely that one can define a notion of Mittag-Leffler inverse sequence of dualizable categories and prove that continuous K-theory in this case commute with limits, with this non-standard limits again. It's different from the naive homotopy limit. In particular, this implies for this nuke tilde. And then one also can adapt the proof to get the result for the nuclear category. Okay, so I still have some time just to briefly sketch the direct computation of K-theory of shifts of modules on the real line, which I think is actually fun, and it's actually quite beautiful if you did not see it before. So we have, maybe I will skip this. So we have this, just to save time, the following notion of a singular support for shifts on C1 manifolds. And this definition, there are different characterizations, and all of them are a little bit technical. So roughly, you want somehow capture in which directions sections can propagate and in which directions there is abstraction for propagation. But there is this results in a notion of singular support, which is a conical closed subset of the cotangent bundle. And it turns out to be coisotropic actually in this generality just for any sheaf. Let's use this notation that for a closed conical subset, some DG ring, we denote by sheaves sub lambda on X, the full subcategory of sheaves for which the singular support is contained in this lambda. Now you can actually ignore this general definition for our purposes, and we will need only the special case of the real line. And if I identify a cotangent bundle with R2, then by Shevara and Shapira, the condition that the singular support is contained in the non-negative part of the cotangent bundle, I mean with the usual orientation of the real line. So this condition basically equivalent to saying that for any pair of real numbers, the sections on the negative ray, so from minus infinity to b of f, are the same as direct sections of f on the interval from a to b. So one can quite formally check that we have a homotopy pullback square. So this category of sheaves can be somehow glued from categories with this singular support conditions. And here, of course, so the functors are just left adjoint to the inclusions. And of course, this category supported on the zero section is just the category of models over A, constant local systems. And this, because all of these functors are localizations, it follows formally that we have still a homotopy pullback square of continuous K-theory, which just means that we have this exact triangle. And now we are reduced to showing that continuous K-theory of this category with support vanishes. And this is a very direct and fun calculation, actually. So we can define this auxiliary small DG categories for which both of them, the objects are real numbers, and homes for the first category, for the category B, homes are only from left to the right, and all homes, all complexes of homes are just identified with this with our DG ring A. And the second category is just has the same objects, but we have only homes from a real number to itself, and no homes between different real numbers. So we have a natural functor from the first category to the second category. And it follows from the description of this category with singular support that we actually have this exact sequence, that this category of sheaves with non-negative singular support can be described as a kernel of a localization. And the fact that this functor is a localization is just basically what we all we need is just that the real numbers form a dense linearly ordered set. So between any different elements, there's some another element between them. All we need now is to check that K-theory of this categories B and C are equivalent. But this is essentially immediate from the definition because both categories have infinite semi-orthogonal decompositions. Already in several lectures during this ICM, we heard the notion of semi-orthogonal decomposition, but here it's a kind of infinite version. You have infinite number of copies of perfect A models, and these copies are indexed by real numbers. And the isomorphism in K-theory between for B and C now basically follows from the fact that K-theory is additive in semi-orthogonal decompositions and also commute with directed colimits. So because we have directed unions, both for B and for C, we only need the commutation with directed colimits. And this actually finishes the proof that continuous K-theory of this category with supported of shift supported in the non-negative part of cotangent bundle, that it vanishes. And by the above, let me just return to this exact triangle. So in this exact triangle, which is in the second line, it immediately gives us that K-theory, continuous K-theory of shifts on the real line is given by the K-theory of our DG ring shifted by -1, which is the loop spectrum. Okay, thank you. I think I will finish here.
Okay.
Yeah.
Thank you very much for your beautiful talk. So I still have a few minutes. So do you like to share with us some of your future project or open problem or anything that you are expecting for the future work?
I mean, one direction which I mentioned, which is very interesting, is to understand this. Let me probably recall to this. I mean, return to this nuclear categories. So, so we have I formulated this result for formal schemes, but there's also a very interesting direction of what happens in the Archimedean setup. So, I mean, formal schemes essentially allow you to deal with rigid analytic spaces, let's say over QP, for example. And you can ask what happens with just usual analytic spaces, for example, complex analytic spaces. So you want to understand categories of nuclear models and maybe which version is correct, and what are their K-theory, and how this relates to the classical, for example, to topological K-theory, to the Linker homology, and so on. And there are some very recent developments, so different people are working on this, including myself. So this is very interesting direction. I mean, already this result, I mean, I have a proof which is very recent, but I mean, it would be nice to have some, I mean, some better understanding of what happens, because the proof is quite technical. And for the for the Archimedean version for complex analytic spaces, I have a very vague picture, so I don't have kind of clear understanding of what's going on. So it's a very interesting subject to investigate.
Yeah. Okay. Yeah. Thank you very much. Yeah. So I think due to the time limit, we are not able to take questions. But if you have any questions, please write an email to Professor Efimov. I think he will try to answer your questions. So let's thank Professor Efimov again for the beautiful talk. Thank you very much.